Assalamu wabarakatuh and good morning to everyone. Okay, today we're going to continue our lecture number 6 titled Concurrent Processes. So, concurrent processes. Concurrent processes, as the name suggests, is a concurrent process, a multi-process or multi-processing. You can describe it, you can describe one analogy like through a KFC drive-through. You drive to KFC drive-through window. Just imagine there's a one KFC drive-through near the near the PJ gates. When you place your order, the order clerk confirms your request, tells you how much it costs, and asks you to drive to the pickup window. So when you order, you can see from the screen there, whatever you order, the clerk will enter your order, and then you can see that together with the total price. At the pickup window, the cashier collects your money and hands over your order. Either you pay by card or cash. Okay, and then you check your order is true. Then this is synchron. Then you go and drive to your home or somewhere else. And this is called a synchronized multi-processing system. Okay. So in this case, you come into contact with two processors, the order clerk and the cashier. Think of your PCs, you have one processor with two core, two processors. Is either way, one processor, two core, or two different processors. And that processor is the order clerk and the cashier. There are at least two more processors to make the system work, the cook and the bagger. Okay. So you have two more processors or two more cores. If you 2 plus 2, 4 processors or 4 cores. Compare the scenario to an information retrieval system. Processor 1 is an order clerk, accepts the query, checks for errors and pass the request to processor 2, which is bagger. And processor 2 searches the database for the required info, like whatever your hot and spicy chickens or original recipes, is up to you. And processor 3, the cook, or we don't call it a chef at KFC, the cook, retrieves data from the database, where chicken to cook if it's kept offline in secondary storage. Once data is gathered, chicken is cooked, it is placed where processor 2 can get it. Okay, remember processor 2 search the database. Okay, processor 2 the bagger check the database and it's placed where processor 2 can get it in the chicken bin. Okay, when the cook done the cooking of the chicken or burger, they pass to the bagger and bagger put on the and then bagger put it on the screen, and processor 2 pass it to the processor 4 or cashier, and cashier deliver you your order. So processor 4 routes the response, your order, back to the originator of the request, which is you. Processor 4 is a cashier, and then the cashier give you all your orders. And before you go, you always check whether your order is correct or not, or something's missing, or something extra they give you. Okay. So what is parallel processing? Parallel processing or multiprocessing is a situation in which two or more processes operate in unison. So two processes execute instructions simultaneously as opposed to the serial processing. You can imagine this as okay. You can imagine this as okay. You have this is the process. Oh, sorry for that. It's supposed to be like this. Okay. Okay, you imagine you have one process, here, and you break down into several thread 1, thread 2, and then sorry, this process can be break down. Okay, this process Sorry for that. And this process you can break down into like several, we call it thread. Thread 1, thread 2, thread 3, and thread 4. So you will go this one in sorry, if you talk in order, this is actually a T1, a T2, a T3, and a T4. So this one is a T4, this one is a T3, this one is a T2, and this one is a T1. So this process, the CPU, one core CPU will process T1 first, and then T2, and then T3 and T4. If you do a serial, this T1, T2, T3, T4 will be processed simultaneously. Let's say you have a core 1, core 2, core 3, and and this is a core number 4. So this is the serial, this is the serial case, and this is the parallel case. Okay, so this is CPU. Imagine this CPU is a one core CPU. Okay, and this you have like 4 cores or something like that. Okay, so parallel processing or multiprocessing is a situation in which two or more processes operate in unison. So it is more than two processes. The basic is two processes or two cores execute instructions simultaneously. The processor manager has to coordinate the activity of each processor and synchronize the interaction among the CPUs. So if you go back here, you have this one, you have T1, T2, 3, 4. So you, at the end, you must synchronize it so it will be in order. So this one is a T4, T3, T2, and T1. So this is a synchronization. Synchronization. Okay, synchronization of T1. So it's in order T1, T2, thread 1, T2, T3, T4. So this is the whole process. Okay, you break down. Okay, you break down. This is the same one. You break down the process. So the processor manager has to coordinate the activity to each processor and synchronize the interaction among the CPU. So this is the synchronization. You done C1 simultaneously, but you have to put it in order T1, T2, 3, T, and 4, so it becomes the whole process. Okay. So synchronization is a key factor in the success of multi-programming systems. So you don't want to mess up, not in order or something, on incorrect value. A system will only work properly if every processor communicates and cooperates with every other processors. You can be a one processor with multi-core or multi-processors. Two major reasons behind multiprocessing is enhanced throughput and increased computing power. So some question may be like, what if there is a communication breakdown between the order between a clerk and a beggar? So they have a communication breakdown. You order a spicy chicken, but actually the beggar give to the cashier an original recipe. And what if the cook produce hot and spicy chickens at full speed all day, even during slow periods? So maybe it's not cooked properly or something. And what would the beggar do if there is no chicken? So you have to it has to inform the cashier, sorry, there is no chicken, and the cashier has to inform you, you can order chicken, you can only order burger or something like that. Okay, so two benefits of the parallel processing is increased reliability and faster processing. The reliability, the reliability is some sort of the integrity or something. Meaning that your work is reliable. It can be trusted. Okay. The benefits are achieved by careful design. The failing processor can inform other processors to take over. Okay. So let's say the beggar, so a beggar has maybe he injured his hand or something. So the cashier can take over the beggar roles. But it will increase some load. The OS can restructure if its resource allocation strategy so that remaining processors don't become overload. Let's say this is the full day, and then let's say in that area only have one KFC with certain, let's say they have 4 workers, and then there is a new residential area being built around that KFC, and there are so many more customers. So the OS can restructure. Maybe you add some more processors, or you break it into the smaller jobs schedule or something, or smaller jobs tasks, so that it can be managed properly. So this is all the OS can do that. And this is all the parallel processing, doing the work simultaneously. So a few ways to allocate the CPU. Number one is allocate a CPU to each job. So if like CPU, you have 4 CPU or 4 cores, you have 4 jobs, so you allocate one to each. Allocate a CPU to each working set. Okay, let's say you have okay, this one, if you have let's say jobs that require, okay, this is the accounting, this is the engineering. Accounting is one working set, engineering is one working set, and the HR is one working set, and so on. So this is allocate CPU to each working set. Subdivide individual instruction, and each subdivision is processed simultaneously. So you divide, so the process, you can chunk it into smaller set called thread and stuff, and subdivision is processed simultaneously. As we see on this, the process is chunked into 4 thread: thread 1, thread 2, thread 3, and thread 4. Oh, thread 1, thread 2, and thread 3, 4, you chunk into the small set. This process chunk into 4 threads. And each subdivision is processed simultaneously, like this one. You do a parallel case, D1, D2, D3, D4, so you do each processor, done that. Subdivide. Increase, it will increase the flexibility, increase flexibility brings increased complexity. Okay, even though this is fast, this is reliable, much more work can be done at one time. So unfortunately, it will also increase the complexity of the system. And there are 2 challenges that are being listed down here: how to connect the CPUs into configurations, and how to orchestrate their interaction. We will see this on the next slide, on the following slide. So there are 3 typical multiprocessing configurations. The first one is a master-slave configurations. The second one is a loosely coupled configurations, and the third one is a symmetric configurations. So we will look first at the master-slave configurations. So what is a master-slave? It is asymmetric. So as opposing to the symmetric, it's an asymmetric multiprocessing system. It's a single processor system with additional slave processors. Each is managed by the primary master processor. Okay, you have a single processor system with additional slave processors. This is one processor with additional slave processors. And you can have 2 or more slave processors, but each will be managed by primary master processors. The master processor is responsible for managing the entire system. This is like the manager, the leader, the master processor. It is really suitable for an environment where the processing time is divided between front end and back end processor. So you have a front end and back end processor. So you have here, this is the master processor. Okay, this is the master processor. It controls two slave processor, slave number one and slave number two. And then it's the input output devices. Okay, so master processor manage all files, devices, memory, and processors. So it manage files, memories, devices. Okay, and maintains the status of all processes in the system. It also performs storage management activities. It schedules the work for other processes and executes all control program. Okay, you have a front end processor. Why is that? It will take care of interactive jobs and quick jobs. You have a front end. You have a front end. Uh, like small and quick jobs. And of course you have a back end. Back end which long jobs. This is actually a long or large jobs, and doing most probably it will doing in batch mode. Okay, so you have here master processor manage all files, devices, main memory, and processors, and maintains the status of all process in the system, keep record of it, perform storage management activities, schedules the work for other processes, and it execute all control programs. So advantage, what is the advantage of master slave? Yes, it's a simple, okay, it's a simple configuration, simple setup, but there are also cons of it. Disadvantage is the reliability is not much better than a single processor system. You have basically you only have one processor, but you break it that processor into master and slave. Can lead to poor utilization of resources and increased number of interrupts. So reliability is not much better. Okay, actually the reliability is not much better because if the master processor fails, if you see here, if master processor fails, all other slave processors or other jobs process will fail. This is single point failure. Okay, the reliability. So the reliability is a single point failure. You have a single point failure if master processor fail. So it also can lead to poor utilization of resources. If a slave becomes free while the master is busy, it has to wait from the master to become free and assign it work. So let's say this is a master processor. The master processor is busy. Okay, the master processor busy doing something. So now it's occupied slave 2, and slave 1 have to wait this master processor to to not become busy or to be free again. But while waiting, it poor utilization. The slave processor doesn't do anything. Okay, it just stay there waiting for master processor to finish its process or work. So it's a poor utilization, and it also increase numbers of interrupts, which means that all slave, okay, see, all slave must interrupt the master processor each time they need OS intervention. So okay, this creates long queue at the master processor level where there are many processes and many interrupts. So slave will invoke, okay, slave will interrupt or the master processor each time they need OS intervention. And then this create long queues and the master processor level where there are many processes, many interrupts. So slave have to request from the request from the OS, and sorry, it will request from the master processor. It will request for the master processor like job 1, job 2, job 3 and stuff, and master processor. This will create a queue on the master processor, and it will become delays and many interrupts, and then also the slave one also will job 1, job 2 and stuff, and it will become a queue on master processor. So heavy loading on the master processor. So this is the disadvantage of the master slave configuration. Now we see the loosely coupled number 2. Several complete computer system with which is its own memory, input output device, CPU and OS. Loosely coupled because each processor control its own resources. You can say that this is a different machines, different machines connected with a network. Okay, you have here you have a PC1, and here you have a PC2, PC2, sorry, PC2, and then here you have a PC3. So each one of these have its own memory, input output device, CPU and OS. Okay, maybe this have a Windows 10, this is Windows 10, this is Windows 8, or maybe this is Linux or something. Okay, a own input CPU and OS. Loosely coupled because each processor controls its own resources. Each processors, okay, they are all connected to the network switch or router or something like that. Okay, and each processor can communicate and cooperate with the others using a network. So loosely coupled, as I mentioned before, okay, this is a processor one, machine one is its own memory and its own input output device. This is a processor two. Think of it as a PC1. This is a PC2, and this is a PC3. So these they have their own memory, they have their own input output device, own resources, and maintain its own commands and input output management tables. So this is the typical, and all these are connected through the all sorry um so so you can see all this is connected via some network. Okay, network. So they have their own memory, own OS, own devices, own resources. And when a job arrives, it is allocated to one processor. It remains with the same processor until it finishes. So the job scheduling algo keeps the system well balanced and ensures the best use of resource using several requirements and policies. Example of new jobs are assigned to the processor with the lightest load. Okay, so let's say you have PC1, PC2, PC3. PC2, maybe the capacity of PC2 only left 80% resources have been used, so 20% left, and PC3 maybe 10% left, and you have PC1, maybe the utilization is low, maybe only 40%, and they have 60% left. And what loosely coupled we do is new jobs are assigned to the processor with the lightest load. So processor 1 fit this description. So if any jobs coming in, so it will go to the jobs in queue, it will go to processor 1. Okay, it doesn't go to PC2 because PC2 only 20% left, PC3 only 10% left. So we go to PC1 because PC1 only 40% utilization and 60% utilization is not used. Okay, are not used. So The third configuration is a symmetric configuration. It is best implemented if all processors are of the same type, meaning that you have, let's say you have Pentium, you have Intel Core 10, all the processors have Intel Core 10, same Windows, same OS, Windows 10 and everything, or Linux. Or meaning that it's basically the same, is duplicate of each other. Advantage over loosely coupled configuration is it is more reliable, uses resources effectively, can balance loads very well, and can degrade gracefully in the event of failure. Okay, it's more reliable because all have the same processors, OS, and everything. Use resources effectively, so you are, I mean, you use whatever in the system, the same system, basically the same system for all, and can balance loads well. So in a loosely coupled, you have to, because each processor have different their own resource and memory, it will create some delays on that to balance the load, and can degrade gracefully in the event of failure. Okay, it's not a single point failure. So you have here the processor 1, processor 2, processor 3, or in a single PC we call it a core 1, core 2, and core 3. And then you have all this connected to the same memory and same input output devices. Okay, this is what we call symmetric, as opposed to asymmetric. This is asymmetric and this is symmetric. This is asymmetric. Okay, asymmetric, each processor different. This is maybe core 10, sorry, Intel core 10, and this one is Intel core i7, or maybe this is AMD or something like that. So this is a asymmetric, it's not the same. But for the symmetric configuration, this is what we call a symmetric. Like all this, like in i10, i10, i10. Okay, so all this is the same OS and everything. So this is a symmetric configuration. It is the most, however, it is the most difficult config to implement because processes must be well synchronized to avoid races and deadlocks. We have learned about race condition and deadlocks in the previous lecture, lecture number 5. Process scheduling is decentralized, so they have no central authority. All is decentralized, or you can call it distributed. There is one copy of the OS, and each processor has access to a global table listing each process and its status that is stored in a common area of the memory. So they have each process has access to a global table listing each process and status that is stored in a common area memory. So you have here, let's say a processor here. You have a global, okay, this is a jobs table. This is the global. Okay, this job 1, job 2, job 3, job 4, or maybe, sorry for the writing, job N. Okay, all this processor 1, processor 2, processor 3, this is the global job table, so they can access each of it depending. So let's say job 1 is in queue, so processor 1 is free now, so job 1 will go to processor 1. Maybe job 2, processor 3 is free now, so job 2 will go to processor 3, and so on. So this is a global table they can access, and it's stated that it's stored in a common area of the memory. So processors use the same scheduling algorithm. When a process is interrupted, its process updates the corresponding entry in the process list and finds another process to run. Okay, since each process has access to all input devices and can reference any storage unit, there are more conflicts when several processes try to access the same resources. It requires algorithm to resolve conflicts. So we have learned all this master slave, loosely coupled, and symmetric configuration. So now we go to the required algo to resolve conflicts and symmetric configuration, or any synchronization. Process synchronization depends on the capability of the OS to make a resource unavailable to other process while it's being used by one of them. Okay, so this is like, okay, you have to done this first. Okay, in order for you to, to paint the house, you must have house first. You must build a house first. You cannot do a paint job first without a house. So that is the logic. A used resource is locked from other resource until it is released. Only then can waiting process be allowed to use resource. Okay, that's why I say, if you want to uh, that's why I say, if you want to do a paint job, you want to paint a house, you must have a house first. You must build a house first, and then you can do paint. You cannot do paint job first, then you build a house. So while building a house, a use resources is locked. So paint job cannot be done. Okay, the paint job cannot be done because you are building the house. Synchronization is important because a mistake could leave a job waiting indefinitely or lead to a deadlock, as we learned before. Example: Processor 1 and Processor 2 finish their jobs executions at the same time. To run the next job, each processor must consult the list of jobs to see which one should run next, retrieve the job for execution, increment the ready list to the next job, and execute it. So, just imagine this analogy. You have getting a number in order to be served at the bank. Okay, the teller pushes a button to indicate the number to be served next. Okay, so you come in here, and then this is the, this is the machine where you push a button to get your number. Okay, go, and then you get a number, and then both go to the ready list to select a job. Both go to the ready list to select a job. So maybe you get the number 74, and so on. This will be this guy, so 74u, and this guy will become 74, and this one is a 75, and so on. Okay, and you have two counters here, counter 1 and counter 2. Okay, let's say processor 1 sees the job 74. Processor 1 see the jobs of 74. The next job to be run, and goes to retrieve it. So it calls number 74, like, the blinking of the screen or something. At moment later, processor 2 also selects job 74 and retrieve it. So it receive a job 74. So this 74 has been called twice with the two processors. Shortly after retrieving job 74, processor 1 returns to the ready list and increments it, moving to job 75. So job 75 will be in the queue. Okay. A moment later, processor 2 increments the ready list, and now job 76 moves to the top and become the next jobs to be processed. So now, because 74, both 74, both has done a 74. It's actually, a conflict. And 75 will never be called on, and 76 we call on first. Okay, a moment later, so job 75 misses a turn because 74 here, and then each increment to 75, and but 75 never had a chance to go to the counter because it will go straight to the 76. Okay, so job 75 misses its turn and will never be processed, while job 74 is processed twice. This is unacceptable situation. So 74 twice, 75 missed the turn, and 76 now go after 74. Either one processor. So other resources where the same problem can occur: memory and page allocation, tables, input output tables, application databases, and any shared resources. When you say it's a shared, it's a global where any processes can access. So this is a potential where synchronization problem can happen. A synchronization mechanism is required to provide cooperation and communication among processes. It allows a process to finish work on a critical region of a program before the other processes have access to it. So, a critical region is a part of a program that must be complete execution before other processes can have access to the resource being used. Okay, synchronization can be made using a lock and key scheme. A process checks to see if a key is available. Okay, if it's available, the process pick it up and put it in the log to make the resource unavailable to the process. So basically here you have okay, this is the resources you have here. Resources. Okay, resources. Sorry for the spelling. uh, okay, you have resources. You have, maybe you have the process 1, you have process 2, and you have a process 3. Okay, okay, now in order to do process 2 and process 3, process 1 must be executed first. Okay, executed first. Okay, and then what does it mean by lock? When P1 enter resources, process 1 enter resources, P2 cannot enter. P2 cannot enter, and also P3 also cannot enter resources. So this is like if you have a pseudocode, you have a lock here, and then you have a, now when the executed, it will be locked. Lock mean P2 and P3 cannot access the resources. Only P1 can. Now P1 access resources. P1 must complete first, must be completed first, and then P2 and P3 can access resources. While P1 access the resources, P2 and P3 are locked. And then do work or something. And then when P1 finish here, P1 finish, so finish, so it will be unlocked. Okay, this is a lock and key scheme. So after P1 finish, so now P2 can access the processes. While P2 access the processes, P1 and P3 will be P1, and because P1 already done, so P3 cannot access the resources. So P2 access the resources, and also it done the same thing, log. While it access resources, it will log from P1 and P3 to access it, and it works. And after it's finished, it will unlock. And same goes to the P3. So the process checks to see if a key is available. If it is available, the process pick it up and put it on the log to make the resource unavailable to other process. Okay, so you only have one. So there are several locking mechanisms. The first is test and set, wait and signals, and semaphores. So test and set. It is indivisible machine instruction known as a test and set, or TS. It tests to see if the key is available. If it sets it to unavailable. So the key is single bit in the storage location whose value is 0 if it is free, 1 if it is busy. And test and set has one parameter, the storage location, and returns one value, busy or free. It takes only one machine cycle. So test set, see whether the key is available. If there is a key is available, it will set to unavailable to other processes. The key is a single bit in the storage location whose value is 0 if there is free and 1 is busy. 0 if there is a key and 1 if they're busy. So let's say the process try to see if the key is available, and if it is 1, meaning that some other process are accessing the resources so that you cannot access that resource. Process P1 test the condition code using the TS instruction before entering a critical region. Okay. a critical region. If no other process is in a critical region, P1 is allowed to proceed and the condition code is changed from 0 to 1. When P1 exits the critical region, the condition code is reset to 0, or so another process can enter. Okay, so 0 if it is free. Okay, 0 if it is free, and 1 if it's busy. And then critical region. Okay, what does it mean by critical region? So you have here a critical region. Let's say you have some so you want to say output hello. Okay, right. This is process 1, hello. Output, and output 2 is Mary. Okay, and this is you have a process 2, and you have this is also a write, and then you write output by, and you have output here John, and this is the main memory. Okay, memory. Let's say process 1 execute process 1 process 2, there is no like scheduling, and there is no priority within process 1 process 2. They can execute each other. So maybe it become, if right into the memory, it's like hell, and then this one by BYE, and then this one is Mary. May will execute May, so this is John, Josh, and then the RYN. So this is all haywire. So what critical region does it? It sets, okay, P1 is a critical region. The critical region of P1 is this piece of code, and critical region of P2 is this piece of code. When you have a critical region, P1 will be execute first. Okay, if you set the critical region P1, so when P1 is executing is writing on the memory, P2 is P1, okay, check whether they have a 0 or 1. If a 0, so P1 will take the key, check 0. P1 will take the key and set the TS to 1, so that P2 cannot access. So it will write here, hello Mary, hello Mary. And then after it finish, it will release back the TS bits to 0. So now P2 can access. While P2 access, it will P2 when first access, the TS bit is 0. And then when it access, it will change to 1. Change to 1. Okay. And now it execute by John. So you see a critical region when this critical when P1 the critical region is set on the piece of code. When it's execute, no other process can access the memory. Only P1 can access, because currently P1 is accessed. So after it finish, so it will release, and then the test set will become 0 again, so that P2 can access the memory and write to the output by John. If not, it will become like this. This is what I mean by the critical region. When P1 exits the critical region, the condition code is reset to 0, and so another process can enter. If P1 finds a busy condition code, it is placed in a waiting loop where it continues to test the condition code and waits until it's free. Let's say P1, okay, let's say while P2 is executing, P1 check, and the test set is 1. So P1 cannot access the main memory. Test and set is a simple to implement and works well for a small number of processes. Two drawbacks of test and set is when many processes are waiting to enter a critical region, a starvation could occur, okay? Because process gain access in arbitrary fashion. Waiting processes remains in unproductive resource consuming wait loops known as busy waiting. So Let's say you have a process 3, process, you have a process 4, process 5, and so on. Want to access the same memory, okay? It might become want to access this one, same memory. So it can be it can starvation, meaning that maybe P4 will never able to access the main memory or resources because process gain access in arbitrary fashion, a random one. So resource wait process remain unprotected, resource coming wait loops known as busy waiting. So B4 will be forever busy waiting or starvation. Maybe they have some more process that can never, because you have to wait by the P1 and P1 or P2 or any process completed. Okay, that's why you have to wait, and it has a risk of starvation. Wait and signal. It is a modification of test set to remove busy waiting. Consists of two operations that are mutually exclusive, wait and signal. Imagine test and set, wait and signal. Wait is activated when the process encounters a busy condition code. So it sets the process PCB to be a block state and links it to the queue of process waiting to enter the critical region. And the process scheduler selects another process for execution. Okay, so this is the wait and signal. And signal is activated when a process exits the critical regions and the conditions code is set to free. It checks the queue for process waiting to enter the critical region and selects one and set its states to ready. Eventually, the process scheduler will choose this process for running. So this is wait and signal. And semaphores is just a flag that has a non-negative integer value. Analogy is like flag-like signaling used by railroads to indicate whether the track is clear. In an OS, a semaphore signals if and when a resource is free and can be used by a process. Okay, let's say if you have semaphore. Okay, you have resources here. Let's say you have this is a resources, and you have a semaphore. Let's say you have two. Each resources maybe at the time resources, two resources can enter at the same time. So let's say you have thread 1, thread 2, and thread 3. Okay, this is the example of semaphore. So semaphore 2 meaning that at one time two thread can access the resources. Let's say you have a T1 access here, and the semaphore counter will decrease to 1. So when T2 wants to access, it checks the semaphore number 1, so I still can access. So it will access the resources and it will decrement to s equal to 0. So when T3 wants to try to access the resources, it sees the semaphore is 0, so it has to wait thread 1 and thread 2 to finish before it can access. So this analogy is the flag-like signaling used by railroads to indicate whether the track is clear. Okay. In an OS, a semaphore signal is if and when a resource is free and can be used by a process. So this is a semaphore example. Non-negative integer value because it's execute as 0 or less if the semaphore counter is less or equal to 0. So it's a non-negative integer. So you have a semaphore 2 meaning that at one time two process can access the resources or memory. Okay, and then when the process number 1 access, the semaphore counter will be decreased to 1. So if like T2 check the semaphore 1, it can access the resources and will decrease the semaphore to 0. When T3 check the semaphore 0, so it has to wait for thread 1 and thread 2 to be finished first. Okay, so that's it for today. Thank you very much, and I hope you understand this. So if you have any question, please post it on to the forum. Thank you very much.